Hey, how are you guys? Today we'll be going over exercise 7.12 from chapter 7, and this exercise goes as follows. It is to construct a PDA for the languages in exercise 6.6. And if we look back at exercise 6.6, it goes as follows. Give context-free grammars for the following languages with the alphabet A, B. Obviously, we're going to create PDAs, not context-free grammars. And for part A, all strings in the form of A to the M power, B to the M power, with M being less than N, less than or equal to N, and N being less than or equal to 2M. For part B, all strings such that the middle symbol is A. And when looking at these PDAs, it's kind of hard to conceptualize them because they are very abstract machines after all. But we envision them with a form of a stack almost, where it's using memory location of a stack to keep track of them. In our case for the program, we didn't use a stack. We kind of used a quicker method, but I think it does just a good job of keeping track of the language behind the machine, and it gives a good rundown of how it's going to work. So for part A, which is again all the strings in the form of A to the M power, B to the N power, such that M is less than or equal to N, and N is less than or equal to 2M. So first thing we need is our two counters. Our two counters are going to be M and N, and M is the counter for A's and N is the counter for B's. Now we're going to see if it can accept empty strings. Obviously, this PDA can accept empty strings, and that's what happens here. And if we keep going, the way this program works is it will read in linearly. So from start to finish, it looks through the machine or the string and checks to see if all the criteria is met. So obviously, first things first is we need to read in all the A's. And that's what it does here with this while loop. It's going to make sure the string is not empty and read in all the A's possible. And it's going to keep track of them with the M variable, and it's going to also update our input string to be without that current A. So it will keep track of them by counting them, and the end result will be that the string that is accepted will be empty by the time the machine's done running. So it'll delete the string. Once it's finished with the A's, it will move on to reading in the B's, and the same thing happens here. Kind of similar to what's happening in A, is it goes through all the B's, make sure that the language isn't empty because we still need those B's, and keep track of them with N's. And then it will reduce the string by removing the current B at the current index. And then the last part is our actual logic or requirements, like up here, this part, the fact that M has to be less than or equal to N, and N has to be less than or equal to 2M. So for those requirements, we just have a simple if block. And since we stored our counters, we just call those guys and we check to make sure that it's true. If it is, that means it is extracted by the PDA, and we return true. If not, we return false. It's just as simple as that. For part B, let's recall that the middle symbol has to be A. That's the only requirement for this string, for this machine. And just to go back a little bit, for this exercise, we're in the language, in the alphabet of A and B, nothing else. So for this part, for part B, we will first make sure that it is non-empty. So what that means is now let's remember that an empty string is even. So if it is divisible by 2 evenly, which means that it's even, it's going to return false right off the bat. It's not going to work for us. So this modulus operator does. It means that if it divides by 2 evenly, which means 0 remainder, then it's going to return false. Otherwise, we're going to look for that middle string and make sure that it is A. And the way we look for the middle string is we have our string, right? Think of it as almost like a list or a tape. And we want to, so we have the beginning and the end. And we want the very middle. We want that very middle piece. and that middle piece has to be A. And then the way we do this is we take our string or our input and we slice it in half, and that's where we get our A, and that's how we get that. And so if it is A, we're going to return true, or in other terms, accept that string into this PDA, or otherwise return false, reject it. Here's an example for the first part and the second part, and all it is just checking to make sure it runs properly, and I can run these really quick for you guys. And we can see now that a simple A is accepted into this language, is not accepted into this language because it doesn't meet those requirements. But now let's say that we changed it to be that it does fit into the requirements. The requirements for the M has to be less than M. And so let's say A, B, B, B. That should be accepted. And if we run it, we get true. Same thing happens here. So if we have, let's say, the empty string, notice that it's false right off the bat, which is what we wanted. Let's say we have just A, and we run it, we have true. Now let's say we have A. Again, true. Now let's say we have something like B, A, B. And if we run that, again, true. Hopefully that shows you guys how these machines work and the inner workings of these two PDAs for this given languages. Thanks, guys.